First of all, good evening to all of you, and thank you very much for coming to this 2017 SETI Institute Summer Internship Lightning Talk series. And delighted to have you here. Delighted that everybody found us and found this location. We're really pleased to be here at SRI International. We're very grateful for this partnership. For those of you who have been at all regular attendees of the SETI Talk series that were previously held at the Microsoft campus, a special welcome to you and a thank you for coming here. I know that a lot more people actually signed up for tonight's event than I see in the audience, so it may be that we've had some issues with directions or location, but this is, I'm very pleased to say, the new home for the SETI Talk series. And after quite some time of looking for new space suitable for this wonderful lecture series, after Microsoft said we're going to tear down our buildings and build new ones, we're very happy to be here. And in fact, I'm even more pleased to be saying to you that we'll be working with SRI. We're going to actually collaborate on this SETI Talks and SRI International lecture series. So the two organizations are going to work together to bring in really meaningful and impactful speakers. One of the changes that we'll be making from the previous series, for those of you familiar, is we do plan to do the talks in the evening because we find that that gives access to more people. We can get more folks attending the talks when they're in the evening. You don't have to deal with leaving work, attending a talk, and trying to get back all inside an hour, which generally isn't very, very easy to do. So the evening series should make it possible for a larger audience and for more people to share in the work that we do and to hear from our other guest lecturers. The other thing is we are changing the cadence of the talks from weekly to monthly. So we'll be putting together a really wonderful series and program of talks. We have programs coming up on the Cassini mission, which ends next month in a spectacular fashion as the Cassini spacecraft crashes into Saturn for the last time on September 15th. We have lots of other programs coming up, and SRI will also be contributing with speaker programming for the series. So as we get more of the programming details, including the dates and times, et cetera, we'll be putting those on our website. We'll be sending them out, the information, to those of you who are signed up for the talk series. And as we always do, we'll continue to be recording these lectures and make them available on our SETI Talks YouTube channel so that you can see them and archive them and look at them at your leisure. So without further ado, I'd like to get into tonight's program and start by introducing our wonderful panel of speakers, and also the gentleman who has really done a terrific job while at the same time doing his own science as a principal investigator and researcher at the SETI Institute, and that is Matt Tescarino sitting to my left. So Matt, thank you for all the work you did to organize yet another wonderful summer internship program at the SETI Institute. Tonight you're Tonight you are going to hear from Sergio Esteban, who is at Cal Poly Pomona, and his mentor is Pascal Lee, who I think is also here tonight. Pascal is in the back with the dog, and the dog actually likes the talks and usually pays more attention than Pascal. So we're very delighted to have both here. And Alaline Teye-Bayan is with CSU Long Beach, and his mentor is Matt. Here with me. And then we have Erbuang Chidamatara from Cal Poly Pomona, and the mentor there is Jeff Smith. And Jeff, are you in the audience? So round of applause for Erbuang and Jeff and Alaline and Matt. We also have Kan Liu, who is at CSU San Bernardino, and his mentor is Virginia Glick, also from the SETI Institute, sitting in the middle there. You can wave, Ginny, your mentor, her mentor. Yes. And Troy Maloney is at Humboldt State University. Mentor is Frank Marchis, who is also with us tonight. And Jose Barrios with Cal Poly Pomona. His mentor is Jerry Harp, who could not be here this evening. And then we have Sean Haas, who's at Humboldt State as well, and his mentor is Uma Gorty, who is here this evening, and Paul Estrada, who could not join us tonight. But I would like to give a round of applause to these mentors who really work hard to support the work of their charges during the summer, and who volunteer their time at the beginning of the season to say, hey, I'd like to mentor and work with an undergraduate researcher. So a big round of applause for our mentors. And an even bigger round of applause for our summer interns. You see? That's right. You got it. Okay. With that, and with the introduction from the dog, I will turn this over to Matt, and thank you very much.
All right, thank you, Bill. I'm going to start by saying a few words about the program. The research experience for undergraduates is a NSF-funded program. We're very grateful to the National Science Foundation for the primary funding, also with some supplemental funding from the NASA Astrobiology Institute. This is an interdisciplinary program. We focus on astrobiology and planetary science, which comprises astronomy, geology, physics, chemistry, biology, and the search for extraterrestrial intelligence. All of those areas of research are represented in our program. This program was founded in 2006 by Cynthia Phillips, who's now at JPL. This is the 12th year that we've run our summer internship program. Jean Char served 3 years as the director, and this is my first year. Rosalba Bonacarsi leads our field trips, which I'll tell you about in a minute. We're also very grateful for the support of Edna DeVore, who's the Director of Education at the Institute. We have a formal partnership with the California-Arizona Minority Partnership for Astronomy Research and Education, directed by Alex Rudolph at Cal Poly Pomona, who helps us to recruit our interns, and particularly to make sure that some of them come from underrepresented and underserved communities in our country. That's an important issue to us. This year we have 7 students whom you see before you. They were selected for this 9-week program. Among the things that we do as part of our program, we focus on educational experience and cohort building. The first 2 weeks we have science talks from mentors and other researchers most mornings. Towards the end we had a career panel with people representing various different career paths that our students might eventually take so that they could ask questions and just get some benefit of that experience. We had weekly meetings to just touch base with each other. They did a journal club where each of the students selected a research paper from the field that they're working on this summer and gave a presentation on it to the group so that we were all enriched, and the students got the experience of researching a paper and giving a presentation on it. Field trips were also an important part of our program. We had some facility tours at Ames, including the wind tunnel and the supercomputer facility. We also took a field trip to Lick Observatory for an evening of stargazing, which is very memorable. There were also this year 2 weekend field trips to areas around the coast here, led by Rosalba, to study astrobiology, habitability, and life detection. Here are some pictures. There is a whale watching was part of it, and also observing wildlife. And an interesting aspect, there was also a lot of geology and environmental science. What they did, though, with these observations of different living creatures and other phenomena was to pretend that they were on an alien world, and to determine what could they know, like, is each of these things that they observed, is it alive? What can they observe about it? So you can see we have the kayaks and the seals and the whale watching ship, all of which were given this scientific life detection sort of treatment. So without further ado, we will introduce the first of our students, and each of these, I've arranged them so that we kind of start close by with Mars and expand our focus out to the farthest reaches of the universe. So we will start with Sergio Esteban. Here's your laser pointer, and here are your slides.
Good evening. My name is Sergio Esteban. I'm a mechanical engineering major at Cal Poly Pomona. My mentor for the summer was Dr. Pascal Lee. And today I'm going to talk about fog on Mars and implications for the extraction of water from the Martian atmosphere. So NASA had a historic meeting on October 2015 called the First Landing Site Exploration Zone Workshop. And the purpose of the workshop was to identify locations where humans can land, live, and work on the surface of Mars. Here is a topographical map. It contains 47 proposed landing sites. Dr. Pascal Lee and his team proposed a landing site on the west end of Valles Marineris here, as you can see. So I analyzed all 47 and evaluated and looked at each one. So here is an example of an exploration zone. In the middle, we have the landing site, a proposed landing site, and then we have a 100-kilometer radius exploration zone. So an exploration zone that has regions of interest that are located within this area. And there are two types of ROIs. There is a science ROI, and then there's ISRU ROI. So science ROIs are specifically to answer scientific questions such as astrobiology, geology, or atmospheric science. We have ISRU ROIs, which are there to use resources such as water, metal, or even dirt for radiation shielding. So resources from Mars are going to play a big role in human exploration. Out of all these resources, water is considered one of the highest resources because it has so many applications to human missions. And NASA has actually done some studies and suggested that atmospheric water extraction is a little bit impractical, but they did the studies assuming low temperature, low pressure. However, special regions with fog might be different. So here you see Valles Marineris on the east end of Valles Marineris, and here is Noctis Labyrinthis. You see this white is ice fog. So as we know, ice fog is composed of ice crystals. And this is more of a morning phenomena, seasonal phenomena that we see here. This is usually on mornings on Mars. So this might suggest that exploration zones in these areas that have a lot of fog might be a better choice. Keep in mind, not all 47 regions have fog that local fog around where, local fog. This process of extraction from fog is a little bit cleaner compared to other ISRU processes that have to handle large quantities of dirt. Also, extracting water from fog on Mars deals with, it doesn't deal with the planetary protection forward and backward contamination that other ISRU processes deal with. So that might be, it's going to be a help for planetary protection purposes. And 0.03% of Mars' atmosphere by volume is actually water. So it's less than Earth, but if you have fog in a region, it can even double or triple the amount of fog in the atmosphere. So just to get a good representation, imagine you filled up 600,000 Olympic swimming pools. That is kind of an approximation of how much water there is in the atmosphere. So here are some terrestrial atmospheric water extraction techniques. As you can see, we have fog meshes that just condense, allow water to condense onto a mesh, and then the water runs down into a gutter, which is then collected and filtered and such. So this requires no power. It's very passive. Atmospheric water generators. These atmospheric water generators use condensation methods or desiccants to absorb or adsorb water from the ambient air. And it's a complicated process, but it might be viable for water extraction on Mars. And there are other processes as well on Earth, such as air wells, dew harvesting, or rain collection. And so far, we're in the process of finding something that might work for Mars. And fresh fog meshes and other liquid condensation systems do not work on Mars, since there is ice fog, not liquid fog. So ice fog we know is composed of ice crystals. So atmospheric water generators for now look promising. So right now, few studies exist on this topic, and future work will mostly focus on designing a viable system for Mars. And your support is welcomed. Thank you.
All right. Thank you, Sergio. Next, we have Con Lu. All right. So here's your time and your laser pointer and your slides.
Thank you. So I just press this button. Oh, okay. Hi, everyone. My name is Khan, and this summer I worked with SETI scientist Virginia Gulick. And today I'll be talking about gully systems on Mars, particularly the West Palliser crater area. So you see an image of Mars, and West Palliser is located at the crosshairs. If you don't know, the blue area is the northern lowlands, and the red area is the southern highlands. And this is an enlarged CTX image of Palliser crater, and it's around 15 kilometers across. And then I used the high-rise DTM to study the gully that I wanted to look at, which is shaded in red. So I made a perspective image of my gully, so you can see this right here. And what's notable about this image is that it cuts across existing bedrock layer, which is right here. And then I used a stereo 3D anaglyph in order to create a drainage diagram of the gullies, which is on my right, or your right. Also notable about this drainage diagram is the integrated tributary system that this gully represents. You have your fingertip tributaries up here, and then your intermediate tributaries, and then your main trunk gullies as you move down, and then they terminate in distributaries. And this kind of complexity is similar to systems on Earth, which are carved by water. And this is a slope map of my gully, and red area indicates higher slopes around 48, maximum 48, and then lower areas are around here, which go from 0 to 20, and the average slope of this system is around 20 degrees. And then next you have a depth diagram of the slope, and the deepest parts are, well, the deepest parts are indicated right here in the blue and the purple, and the depth, maximum depth is about 60 meters. And the capacity of this gully is about 6 million cubic meters, approximately 2,312 Olympic-sized swimming pools. And then in order to compare what I did in ArcGIS, which was the last slide, I used MV in order to draw transects across my gully. And these transects give us a cross-section right here. And this cross-section is from, oh, I can't even see it. It's red crosshairs, but it's up there. And the depth of this seems to be 50 meters at this part of the channel. And we combine all these little cross-sections together to get an approximate volume. And then here is a longitudinal profile of my gully, and you see the concavity of the gully, and the gully is around 2 kilometers long. And this summer, I also used chrism analysis to look at the mineralogy of the gully. For example, in this case, I was trying to look for H2O ice in my system, and the regions of interest after I applied the filters were in the red right here. And I pulled out the spectra from each pixel, and they're represented here. These are different locations. So H2O ice has a diagnostic feature at 1.5 microns, and it's a broad absorption feature. And I was looking for that, but as you can see, it's not really consistent. I might have had something here, but they're too broad, and there's nothing showing up here and here. So in conclusion, the complexity of the gully system, so the integrated tributaries and the concavity of the gully and the erosion into the bedrock suggests that they were carved by water. And continuation of this project, you can do more 3D modeling, you can do more chrism analysis, obviously, and statistical analysis of the other gullies in Palliser. And I would like to say thank you to Virginia Gulick, Matt, and Natalie, who's not here, and everyone in my office for helping me with everything. So, yeah.
Okay, next we have Alaline Bayan. pointer if you want it. And you use arrow keys, and this tells you how much time has gone.
Good evening. My name is Alalin Bayena, and I'm from. Good evening. My name is Alalin Bayena, and I'm from Cal State Long Beach, and I was working on giant propellers on this summer, and I work. My mentor is Matt Tescarino. The unsuccessful attempt of the embedded moon to open the circumference gap can bring a disturbance, and that disturbance we call a propeller. And the propeller is located on the outer ring of A, on the Saturn, on here. All the giant propellers are found over there. And the propellers can be small. That is, when the small moon try to open, it might not be a full gap, so that brings a local disturbance. That is what is seen here on the upper picture. And the shearing flow of ring materials can make a propeller shape that is surrounded by the embedded moon. And this picture shows that propeller shape. So far, scientists were studying on tracking the orbit of object on a free empty space. But now they are just trying to track object moving inside the disk. And the whole aim of this propeller study is about that. And propeller size can be different. It can be small, because of a small embedded moon in the disk, and also can be bigger. A big embedded moon of 1 kilometer in diameter can create a giant propeller. And I have some pictures of giant propellers. For instance, this is a Earhart, and you can see a picture from Cassini image. And these propellers were discovered, many of them were discovered during the equinox of Saturn. Saturn has an orbital period of 29 Earth years. During this time, there are 2 times when the sun shines edge on the ring. And during this time, these propeller structures cast a shadow, and they track this shadow back to find those big structures, which we call giant propellers. And here we have the lit side and unlit side of this propeller. We call this propeller Santos Dumas. And this one is the lit side, and this is the unlit side of. For the better comparison, I put it on the top of the other. And we can see it. This is the lit side and the unlit side. And I was working this summer on this image. It's a raw image from Cassini spacecraft. And I use the caviar to just access these images, which are on area numbers. I access this and work on these pictures by image analysis using the ideal programming. Yeah. And this is the actual project. The project I was doing was just make a rectangle section on the propellers and take the XY coordinates. Then from the coordinates, it's possible to find the radius grids, and using the interpolation method, we find the radius centers. In the same way, we find the longitude centers for both the lit and for the unlit side. Once we get these parameters, we use this to find the method of comparison of the lit and the unlit brightness. To do this, we go for the unlit side and take the radius we already calculated. Then we go back to find the corresponding Y value in the lit side. We do this also for the longitude. Once we get this longitude and radius, we subtract appropriately from, we subtract the R center and L center. and we get numbers. We use the interpolation of linear fit and find the xy of the lit side. And the very reason of doing this is because the propellers are orbiting in the lit and unlit side with different time span. They change positions, and we need to get the same region on the propeller that have the same component for brightness comparison. That is a project, the main aim. Thank you.
Next we have Troy Maloney. Here's a pointer, arrow keys, and your time is there.
Hello, everybody. My name is Troy Maloney, and this summer I had the honor of working with the international team of researchers, all involved with the Gemini Planet Imager, or as I will call it from here on out, GPI. So the goal of GPI is to directly image young Jupiter-like exoplanets with the 8-meter telescope Gemini South in the Chilean Andes. GPI uses a coronagraph and advanced adaptive optics system to image planets with a contrast of up to 1 million times dimmer than the stars that they orbit. So why do we care about direct imaging other than it can get us really cool images of planets orbiting other stars? Well, for one, it allows us to see light that is emitted directly by planets themselves, not contaminated by the stars that they're orbiting. Two, it opens up the parameter space to different types of planets that we would not be able to see with other methods, namely large or massive planets that orbit really far away from their parent stars. So before we can look at pretty pictures of exoplanets, we have to do a lot of data processing, and that's what I was involved with this summer. So before I came onto the project, the GPI team had developed a Python package of functions called PyClip. It was able to do a couple of different image processing techniques, but then there was something called RDI, which PyClip was not able to do yet. But then they recently implemented it into PyClip, and my job was to test if this new PyClip RDI was as effective as the older methods. So RDI is a type of image processing utilizing something called a reference image library, which is basically just a library of images of stars. And basically this was just all of the images that GPI had collected. This was about 15,000 images. And what you do with RDI is you find the images in the library that are most correlated or most similar to the images in your data set, and then subtract those from your the science image, or the one that you're trying to clear up. So before you can do good RDI, you have to weed out the bad reference images. And these are things like some sort of failure of the telescope, or maybe there's an object present in the background of the image, or there's a stellar companion or a planet orbiting the star. And to get the best results with RDI, you need images of stars that are uncontaminated by any of these things. So a lot of what I did was looking through the library and trying to weed out these bad reference images, because there were, even after removing the ones that we knew about, there were a bunch that we didn't know about. So I developed a little program that would help us identify these unmarked bad PSFs, or bad images. So after you get all the bad PSFs out of there, you're able to do some pretty cool stuff and get this type of you can get these images where each frame shows another, like, more reference images subtracted from your science image. And you can see that after about 200 images taken out, we get a pretty clear picture of the planet 51 Area B. So this is on the left there are images that I generated with PyClip RDI, and this is comparing them to previous iterations. And you can see that at first glance, it looks pretty good. Looks like PyClip is working pretty well. It's hard to say whether it's working better or worse than previous iterations. We have to, now the plan is to test and see if we can numerically, or if we can quantify how well RDI does compared to the other iterations. So in conclusion, it works, but we don't know how well yet. We can't say definitively how well it works. And that's future work for the people after me. But what we did get out of this was a new tool for cleaning up reference libraries, which is great because PyClip is open source and available for use for any instrument that uses a reference library. And these include not only ground telescopes, but also upcoming space telescopes like James Webb and WFIRST. So, thank you.
All right, great. Thank you, Troy. All right, next we have Erbwong Chittimatara. All right, there's a pointer if you want it. Arrow keys to do the slides, and this tells you how much time.
Okay. Cool. Okay. Hi, everyone. My name is Erbwong Chittimatara. I am an aerospace engineering major at Cal Poly Pomona. And this summer, I worked with Jeffrey C. Smith on optimizing the TESS planet finding pipeline. TESS is a new NASA exoplanet finding mission called stands for Transiting Exoplanet Survey Satellite. It will be an all-sky survey that will observe stars tens to hundreds of light years away, and will be observing 10 to 100 times brighter than Kepler targets. And the proximity of its observations will allow for easier follow-up measurements for planet characterization, such as mass and density. It's expected to find about 1,000 planets smaller than Neptune's and dozens of Earth-sized planets. And the pipeline that it uses for data processing will be a pipeline adapted from the Kepler mission. So the specific component of the pipeline that I worked on this summer is called Transit Planet Search, or TPS. It's the component of the pipeline that detects transit signals. And how it does that is that it folds the light curve upon itself to identify signals where they stack up on top of each other and amplify it. And then it is then compared to a simulated transit model to account for any observational characteristics such as limb darkening. And in this picture, each of those red lines are identified as transit signals. And this would be the smooth transit signal curve that we would get. So we want to validate TPS by determining certain truth values for each target, which is our true positives, false negatives, and true negatives. And we do this by comparing the simulated data that we know to be our ground truth with the simulated data in TPS. And from here, we can figure out our recall and precision values for each target. And what we do is we would plot it against what's called a multiple event statistics. And what this tells us basically is how strong our signal is and how confident we can be in our signal. Since we don't have actual flight data, what we can actually calculate is expected mess given our ground truth. And that is the equation for it that we use. So there's a couple of parameter changes that we can work on to try to optimize TPS. One of the examples that I use here is changing the minimum transit detections from 2 to 3. And the importance of this is that if you have a minimum of 2, it allows for more stuff to get in and possibly increase our false positive rates. So we try to see what differences we can get by increasing that minimum to 3 transit detections. And we would plot it, and we would compare it to a theoretical sensitivity performance, which is that red line at 7.1 sigma. And as you can see, there wasn't much of a difference that we saw, which was kind of not what we expected. We kind of expected that the recall would be higher in a 3 minimum transit. We don't know. We would have to further investigate why this is so. As you, from our previous slide, you can see that we did calculate our error bars, and this is the equation we used for it. We multiplied it by 1.96 to ensure that we're looking at the 95th percentile of confidence, and it's proportional to the number of targets we're able to inject into it. And the more we are able to inject, the more we can reduce our values, our error values. We can also plot recall as a function of both mess and period. And what we weren't expecting is sort of the inconsistencies between this plot and the previous plots. And that will need further investigation, specifically why it doesn't look quite the same. We also measured the sensitivity in the entire pipeline, not just TPS, but the data throughout the pipeline. Sorry about this. So this is our actual graph that we used. I mean, this is the actual plot that we plotted out, and it's, as you can see, it's doing quite well. So what we know is that TPS is detecting planets, which is a good thing. It's always good to verify and validate that what we're doing is actually what we're expecting. And we were able to experiment with various other parameters that we adjusted. This was just one example. And really, to do all this, it required a supercomputer, but we only had one workstation to really work with. And I want to thank everyone, my mentor, Jeffrey C. Smith, especially Matt, our director, and everyone that supported us this summer. Thank you.
All right, great job. Okay, next we have Sean Haas. All right, laser pointer, arrow keys.
Hello, everyone. Hello. My name's Sean, and this summer I worked on a project concerning computational modeling of protoplanetary disks. So first off, what's a protoplanetary disk? So they're disks around young stars that form planets. And they're primarily composed of dust and gas, and they're observed as spectra in the infrared range. As an illustration, the top plot here shows what we'd expect a spectra of just a star to be. Then here's the same spectra if we had a star surrounded by a continuous disk composed of dust. What we observe in protoplanetary disks, however, is a gap between a visible and an IR bump, and that gap's due to a space between the star and the disk itself. So I'll come back to plots like this that we generated using computational methods and compare those. So the other aspect of protoplanetary disks, or the aspect that we cared the most about, was dust phase, and specifically how that evolved in time. And there's 2 ways that dust can change in a disk over time, by either interacting with other dust in the disk or interacting with the gas phase of the disk. Now, dust is important because that's what actually forms into planets. And if we're able to understand how the dust evolves, then we can understand more about planet formation, which includes understanding the fraction of stars that are able to form planets and what chemicals are available for planet formation. And specifically what we're going to be talking about tonight is the radial drift interaction in the disk. So radial drift is where dust grains get pulled in towards the star as they grow in size. So if this was the only force acting, then we'd expect there to be no planets, because as the dust grains increase in size, they get pulled out of the disk and deposited into the planet and be gone. We wouldn't have grains to form planets from. However, we can directly see this isn't the case because we do in fact form planets, and we can see through observations I'll show on the next slide that we're retaining larger grains than we'd expect in a pure radial drift case. So there's a little bit of a confusing plot because this axis is reversed, but up here, basically this is dust size from small sub-millimeter size to large centimeter regime size dust grains. And this is for a whole set of different star forming regions across different time scales as far as age. So we have a 1, 2, and 3 million year samples. And as we can see, if we were only dealing with radial drift, we'd expect the grouping to be up here in the range of having smaller particles. But we're seeing that even at 3 million years, through observations, there is still a retention of large dust grains. So one way we can account for this, and that my research tried to examine if this was the case, is having fractal instead of spherical grains. So currently, most models assume that dust grains are spherical for simplicity's sake. However, we know this isn't the case. As an example of this, this image is a picture of a dust grain taken from our own solar system, and it's clear to see that that's not spherical. So how we model these fractal grains is through a parameter called porosity, which is basically a measure of the void space compared to the solid space, where a 0 for a porosity would be a fully solid sphere, and a larger number like a 0.9 would be something that's very fluffy, so almost completely void space. So the key question here is, do fractal grains affect dust disk evolution, and if so, how? So the first model we ran was for generating unobserved spectra. So going back to the first slide where I showed sample spectra. And what we found was by increasing the porosity, the curve of the spectra shifted considerably in the lower wavelengths, but didn't change a lot in the higher wavelengths. And what's important to note here, so our sample here we used 70% silicates, 16% carbon, and a small trace of ice. So the resonance feature here is due to silicates. In a lower porosity case, the silicate resonance feature gets washed out by carbon emission. However, as we increase the porosity, we were able to keep the silicate emission while also having a carbon component that was not washing out that feature. So this is important because we can solve the problem of having both silicates and carbons by invoking porosity in our grains. The other model we used was our actual evolution model, which modeled the change of the dust composition, or the change of the dust component in the disk over time. And so this graph shows over 3 time epochs, so the 1, 2, and 3 million year epoch, how the surface density of dust changes in different radial bins. And as we can see, this being the solid case, this being the porous, the green line at 2 million years, we have a much higher surface density in the porous case than the solid. So the takeaway from this is, in fact, porosity does matter. It changes both the observed spectra from the protoplanetary disks as well as our dust retention and our radial drift. Thank you.
All right, and finally we have Jose Barrios. Laser pointer. Sweet. And arrow keys. And this tells you your time.
All right. Good evening, everybody. My name is Jose Barrios, and I had the pleasure of working with Dr. Jerry Harp this summer with surveying of pulsars, quasars, blazars, and exoplanets. So this is the Allen Telescope Array up in Hat Creek, California. And this summer, I got to work with data collected from 2010 to 2011. Too close? Sure thing. For a project that was known as SETI Quest. And we wanted to conclude with, or conduct with this data was a new type of analysis on it, searching for radio astronomy objects. And this process is known as autocorrelation. This was done because certain radio frequencies are known to be natural phenomenon, coming from natural sources like, quasars, blazars, and stuff. This was done because the goal is to catch radio frequencies that just so happen to go and hit the Earth's in a certain direction. So it's sort of like hearing leaking noise coming out of a room, if that makes sense. So our motivations are: assume that there are extraterrestrial intelligence that can build and create beacons, and knowing these sources and that emits information out at a kilohertz or a gigahertz of bit rate. So they could possibly put them next to these pulsars, quasars, or blazars, and in hopes of, if someone were to look there, they would find it, what they're looking for, after clearing out all the noise. And we would also like to use this autocorrelation to perhaps find maybe new physics that hasn't been discovered, or alien beacons. Who knows? So the process, of course, data collection, collecting tons of data from the ATA, so much in fact that I had to help reduce it while still finding the optimal signal-to-noise ratio, or SNR. So what I did was I wrote some code that helped us analyze this data, and hopefully better than previously done before. Yeah. So to analyze this data, we used the autocorrelation process, which is a process that correlates a waveform with a delayed version of itself. And so what you do is you superimpose one image or one signal either in the time or frequency domain, and then wait for it until you get a repetition, and then you get a hit on your autocorrelation graph. So, yeah, so this process shows us that the wave is self-similar, and that the, that the distance between the peaks is the period of the waveform. So what I did to get a good signal-to-noise ratio was we averaged over 8 million points 8 million points from the tons of data that we had, and then I averaged over another 1,024 points. And we also had to, or we were able to truncate the value even more, because thanks to autocorrelation, the negative x values are just a mirror image of the positive x values. So we don't need all of that. So that is the equation for the p-norm, which is what I used as well. So the p-norm, what that does is that gives us, or helps us to get an optimal signal-to-noise ratio, and it's a sort of a summation. No, it is a summation, and then we divide as well inside by the number of things that we summed over. So we wanted to find a value besides infinity that would give us the optimal value, and through the sources, or through using just models and simulations, we found that the number was 5. I didn't even get to the cool parts yet, so we're just gonna go ahead and skip that. So we had to notice interference. This is a satellite called GOES. As you can see, their peaks, we found the delays ought to be within, like, what is that? 1,230.4, something like that. And next I will show, that's a KOI, which is a possible planet. As you can notice, they look exactly the same. I also found that the periods all happen to be the same. So unfortunately, when you're doing with radio astronomy, you have to deal with interference. And it's sort of like a lens flare when you take a picture of a camera. Or if you've seen a J.J. Abrams film, you know what it's like. So interesting prospects. This is a pulsar. As you can see, there's a very small peak here. After we did some processing, we found that not only did it increase, but it's above 5 standard deviations. So when you do, what is it called? Statistics. You know that 5 standard deviation is very hard to come by, and it's really good that it's probably not just noise, where some other noises did disappear. Oh man. Well, I was able to also look at the WOW field area, and we found some very interesting things. Still not sure. We're still looking into it, and yeah, it's really cool. So big takeaway, autocorrelation is really great, especially when you use it with combinations of other detection methods. Thank you for your time.
Okay. Thank you. You guys all did great. Yeah, I think you did. We are now open for questions. So I think there is a mic to be passed around the audience,
right
and
here.
all the students up here have mics. So yeah, questions.
Okay. It seems like you had very limited time to get into these really deep experiments from what we're listening to. So how did you all do that? How did you all jump in? What was the role of your mentor in showing you, what were the methods and what was the process? Because you couldn't go from 0 to 60 in 2 seconds. Kind of interested in that.
So yeah, for me, as soon as we got to SETI and we got everything set up, Dr. Jerry Harp sat with me a lot and showed me some things about how to code, because I knew a little bit of code, not enough, I guess to say. So I had to pick that up pretty quickly. And then a lot of reading, just about radio astronomy that I had not known before and whatnot. So that's really what he did.
Okay. Not everyone has to answer. Maybe one other person if they want to, but.
So for me, I was sent reading material beforehand, and it wasn't. Then the goal wasn't quite necessarily to understand every detail of the paper. It was just to get the bigger picture of what we're trying to do. And then, like Jose said, during the first week, our mentors sat down with us and kind of really showed us, what we're doing and how to do it. For me, I had coding experience, but it was a while ago, so it was something I had to kind of just get into and try to, I guess, bring back all the memories that I have for coding. Yes, yeah. So it wasn't part of my major or anything, but well, one thing I forgot to mention was I am minoring in astronomy. So this work was of great interest to me as well. So.
Okay. Other questions?
Other questions?
Question about the modeling of the protoplanetary disk and that dust grain. You showed a photo of the dust grain. Where'd that dust grain, how do we get that?
So that was a dust grain from our own solar system. So I'm not completely sure if that was from an impactor or from a mission like Stardust, but that was from our own solar system, and we believe that's an accurate analog to dust in other planetary disks, because our solar system formed from the same process.
This is for all of you, but Khan, maybe you can answer this. You had a null result with your experiment, and sometimes in science a null result is just as important as a positive result. But I wanted to know how you interpreted that null result for yourself.
So I think you're talking about CRISM, right? When I was doing the CRISM spectral analysis. Yeah. The good thing with CRISM was that in that image, each pixel had its own spectra that I could look at. So just because I looked at a few and it told me I had nothing, I wasn't quite disheartened, because I knew that was like picking up a few sand grains within an entire beach. So I knew if I did some sort of combing, I might hit something. If not, it would have been fine. Just look at another area.
Any other questions?
So I had a question on the propeller features in Saturn's rings, and that was: is there a cutoff point between, say, is there an endpoint to what can be the largest propeller before other phenomena take hold and you end up getting a small moon formed? Did you find sort of a boundary condition for how large these propeller features can be?
Giant propellers, they are formed by embedded moons in the disk. In the disk.
To speak very loud.
By embedded moons of diameter like 1 kilometer and above. These big embedded moons can create giant propellers of size of long radius 6 kilometers. And there is also azimuthal length of thousands of kilometers. and yeah, they can be large as 6 kilometers in radial distance, and azimuthally thousands of kilometers. They can be as large as that. Yeah.
And I had a different question for Khan, and that is because you were doing the CRISM spectroscopy. Can you explain what that is for the audience who may not be aware?
Oh, okay. So CRISM took data in the IR and the visible near IR spectra. It was pointed at Mars. It was aboard the MRO, and it collected data of the surface, and it tells us mineralogy based off of the reflected spectra.
Okay, and how? What was the best resolution image you had of the features you were looking at? Because clearly you're getting some incredibly detailed, up-close images of these gullies and features on Mars.
So I think you're talking about the DTM. The DTM has great, fantastic resolution. I mean, that's what their experiment was for. It's about 1 meter per pixels, which is really great resolution. But for CRISM, it's a lot lower. It's around 18 meters per pixel.
This is for Troy. You're going to have to forgive a very naive question because I may not have understood something about your presentation. You showed how to detect planets without using a chronograph. Is that what you were doing? Basically, you subtract the star through CRODE. Is that what you were doing?
No, all of the images were taken with the chronograph.
Okay.
Hi, my question is for Sergio about the fog on Mars. You talked about how much water there is total in the atmosphere. What kind of conclusion did you get about if you go to a place that's foggy, do you think you might be able to get enough water to be useful?
Yeah, so most of this has to do with actual calculations of a working concept. So far, we are looking for that actual concept. So we can't do real calculations like volumetric flow rate and expected yield and efficiency and like that. So until we have an actual working concept, then we're going to be able to see how much we can yield from the atmosphere, and particularly more with the fog. But in principle, we should be able to extract more in foggy regions than a region that has a clear atmosphere.
In terms of these young men sitting here who might think about doing this someday, they were wondering if you get paid a stipend.
The answer is yes. There is money involved.
Good.
Enough to cover your expenses, I hope.
I wondered if any of you have were motivated to change your course of study based on your experiences this summer.
I'm thinking about that astronomy minor. Space is actually very beautiful, and I'm just captivated by the subjects that all these scientists study, and I just want to know more about it, so I might consider that.
Any other answers?
Or if you're thinking of, pursuing further higher education in your current field.
So not exactly changing my major, but maybe putting a different emphasis on it. While I did enjoy the radio astronomy, I'm not 100% sure if that's what I want to do later on in my future. I kind of hope to use my physics degree to probably, well, answering the question if we're the only, intelligent beings out here, maybe something that's more impactful right now, like helping just the planet in general. So that's what I got.
All right, Tom?
Oh, so a question for Sergio again, fog on Mars, and Robert Zubrin has written, or he's promoted in situ resource utilization. Is the plan, if you do this, is the plan to the human crew launches knowing that they're screwed if it doesn't work, or or is it just a nice to have that if it does work, maybe the next guys would use it? I mean, how would this evolve?
Yeah, so if it doesn't work, then we're all fired, obviously. So, but you know, there's always testing here on Earth, and yeah, right now it's mostly in our heads. Thinking of the design is going to be the challenging part, but obviously, as an engineering major, we want to create something that's going to be reliable, and having the evolution of such an idea is almost guaranteed. Everything we have has evolved. Otherwise, we would still have a giant brick phone in our pocket right now. So, hopefully that answers your question.
All right, Billy, you want to bring us home?
Yeah, just one last question for Sergio. We all love the fog. Fog is great, but maybe it's because of our base here in San Francisco.
There you go.
Anyway, so you were looking at the landing sites at the 47 proposed
47 proposed landing sites.
And did any of your, I mean, obviously your analysis was focused around the fog. Did you, in your endeavors, come to some conclusions that there were a few that were really the more interesting and should be selected by NASA?
Yeah, actually, surprisingly, there are a lot of good sites that I saw. And keep in mind there were bad sites, in my opinion. There were a lot of equatorial regions there. For example, Dr. Pascal Lee and his team chose west end of Valles Marineris, which is high altitude, and something like this, fog machine. If there is, like, Valles Marineris is known for the largest canyon system on the solar system. There's fog frequently happens there. So choosing a site where there's a lot of water might be very, wise compared to somewhere that's very high latitude, or somewhere that is very, plain, no local in situ resource utilization for that purpose.
All right, and Pascal's probably not listening to this, so I just want to know if he tried to influence you in any way that his site was perhaps the best site, since he's one of the proposers.
All right. All right. On that note.
Okay, well, thank you very much. Obviously, a lot of hard work was done this summer by these young students, and I think it's also even more challenging to try to condense that into a 5-minute little pitch, especially when you have the head of the program here with his alarm going off. And you're like, uh-oh, I'm out of time. So I thought everybody did a wonderful job with a tough challenge to tell your story of a whole summer's work in 5 minutes, but very good, concise presentations, and obviously a lot of hard work and a lot of good learning that went into the programs you each individually were involved in, and I think a good representation of the science of the SETI Institute that, as Matt sort of organized the talks from our close neighbors like Mars out into the cosmos, that's pretty much our domain. So I'd like to just thank all of our students for the great work they did this summer, and again for the mentors for all their coaching and help, and thank all of you for joining us here tonight. And we'll be looking forward to seeing you again with our next SETI talk coming up in September, the details of which will be forthcoming. So thanks very much, and congratulations to the REU students.